Let me share that screen. Right, with a bit of luck, you can see it says meteorology on the screen.
Yeah.
Yep.
Hey, that's it. By the way, well, there's nothing more than that. That's it. This is how we spell it. End of lesson.
Change my life.
You see those two clouds at the top? That's what we're
Job done. Yeah, there's some classic cloud formations there. Okay, meteorology. Is it going to move? Come on. It's done this before. The slide won't move whilst I'm on Zoom, and it jumps. Yeah, the clouds are moving. Come on, come on. It's thinking about it. Right, I think let's jump the slide. Why is it doing that? Okay. I'm going to just try and I'm just going to start it again. Wait, bear with me. No, it didn't jump a slide. No, it's okay actually. It's fine. Right, I'll do it again then. Oh, for God's sake, it's done that again. He wanted to do that.
Well, actually, what Paul is not saying is that he's warming up like a heli.
Right, we'll try it. We'll try it again. It's just so slow.
Oh, warm.
Well, anyway, meteorology. Right. Yeah, thanks, Ross. Cheers, buddy. Okay, we'll go on to this anyway. It's fine. All right. So this was all about just talking about the different layers of the atmosphere. Now, I should stress, have a look at the scale over here, by the way. You can see we're talking about many, many miles. And when you think about it, we only fly, oh my goodness me, right down here.
Yeah.
This little itty bitty bit down here, don't we?
Yeah.
But it's just for people to understand the different layers of atmosphere, the troposphere, stratosphere, mesosphere, and thermosphere. And most people have heard of things like the stratosphere, but not many people have heard of the others. But they're very, very high altitude, don't affect us as helicopter pilots. You can see that I put down here a classic commercial jet would fly at somewhere around about 32,800 odd feet, somewhere around about 10 kilometers up thereabouts. Just about makes over the top of Mount Everest.
Yeah.
And was there anything in particular I wanted to say about that? No. What's it? I'll tell you what is interesting. Look how high weather balloons make it sometimes. Right up to, so, you know, 30, 40 kilometers up in the sky. Pretty cool. Now, the other bit was hiding under, just need to move you all over, you can't see that, is how normally we expect the temperature to decrease with altitude. And we can see it does. For instance, if it starts off at somewhere around about 15 degrees, it starts to decrease. By the time you get up to, you know, that sort of 32,000 feet, it's down to, can anybody tell me what it drops down to there?
Minus 1653.
Getting close.
52. 57.5.
Oh, who said that? That's very close.
Tony.
Well done, Tony. That's pretty damn close. I'm pretty sure it's minus 56.5 degrees.
Damn it.
From memory.
Wow.
This is where Tony's going to, Tony, look it up and then to let us know. Yeah, so I'm pretty sure it's minus 56.5.
I think you're right. I think it is 56.5, yeah.
Yeah. And then it kind of is fairly stable at that, very chilly. And then it warms up. But when I say warms up, of course, so if you look, it never quite makes it really above zero. But it's weird, isn't it, how it then starts to get warmer. And then, of course, it goes really cold when you start getting up to the edge of the atmosphere, etc., and beyond. So, yeah, we always, we know, because we teach with altitude, normally temperature decreases. That's it, full stop. However, it does actually warm up and then it cools down again. But this is way beyond where we're flying. It's just one of those things that's out of interest. Okay. So properties of the, physical properties of the atmosphere. And this is, as we say, just the lower atmosphere where we're kind of mucking around, flying, etc., and living. Did everybody know that nitrogen was the most abundant gas?
Yes.
So anybody that's not done any sort of study or met or remembers anything from school, you usually would say either oxygen or carbon dioxide because of all the global warming and the excess of carbon dioxide being pumped out. And when you actually have a look at the volume, the percentage, it's tiny, isn't it? It's not even 1%. But of course, the actual quantity of it is a lot, but it mustn't be too much, as we know. It's got to be a fine balance. It's like the water vapor. It's really actually not a lot, not as much as we might think. And oxygen, yeah, 21%, but all the rest of it's all nitrogen, and then the rest of it is all the various other gases, isn't it?
What's interesting is when we learn met about the composition of the atmosphere, they always quote nitrogen, oxygen, and carbon dioxide, but argon is higher than carbon dioxide. So I wonder why.
Yeah,
that's not mentioned.
I mean, gosh, I can only say because we want to know. Well, this is the most abundant gas. Makes up 78%. Then oxygen virtually does the rest of it. That takes you up to 99%, doesn't it?
I think so. Carbon dioxide knocks argon off the list, and they say carbon dioxide and other trace gases and water vapor. So it's just kind of it's odd that gets priority, but maybe it's because it's so recognizable.
I was going to say, I reckon because it's recognizable and everybody knows about carbon dioxide, don't they? You know what we breathe out, what trees breathe in, etc., etc. All that sort of, I don't know. I guess about all I can assume. Any questions there at all? Jonathan's asked an interesting question. I don't know, you probably might not be able to hear Jonathan. He said, why is water vapor variable from 0 to 4%?
Depends on temperature, I guess, and water evaporating to become vapor.
Yeah, absolutely, because of course it's just down to the humidity, really, isn't it? Yeah. The moisture content there. That is a variable, as we well and truly know, whereas the others pretty much don't vary at all, do they?
That's the only one that varies then.
Yes, that's it. As far as I'm aware of, anyway. Yeah, it's the only one that varies. It makes a big difference. It makes a difference to whether the helicopters fly nicely one day to not quite so well on the next day. Yeah, so when the air is cold, crisp, clean, and not a lot of water vapor, they fly really nicely. The rotors work amazingly well. It's got stuck again. Come on. Is it going to move? It never used to do this, but it does it now, I've noticed. There we are, right. You watch, it'll jump several screens. Okay, the International Standard Atmosphere. So we can see the first allegedly standard atmosphere models were developed back in the 1920s in both Europe and the United States. The slight differences between the models were reconciled. So they had separate ones back then, and they're obviously just fractionally different. There must have been a slight disagreement as to what was standard. And they're internationally accepted models introduced in 1952. So not as long ago as you think. It's not as long ago. But it was introduced by the International Civil Aviation Organization, and it is spelt with a Z. So that's sometimes a quiz question, by the way. But I'll try not to do it this Christmas one. Everybody know it now. And can anybody tell me how this ISA was developed? How did they get a standardized atmosphere? Well, I do believe they looked at possibly a country like the UK, looked at all the conditions or the weather for the year and just averaged them out. And it turned out the average temperature was 15 degrees with a typical sea level pressure setting of
1013.
Yep, 1013.2, and it does go further than that, but 1013 is fine, or 1013.2. And with a pressure that decreases by 1 hectopascal, as we call it, every 30 feet. And a temperature decrease of
degrees per thousand.
Yeah, because it doesn't always do that. And in fact, it doesn't very often do that. It's always something slightly different, isn't it? It's not very often that the temperature is 15 degrees out there and it's 1013 hectopascals and it decreases by 2 degrees per 1,000 feet. There's always a bit of a variation and we're often trying to work that out, or sometimes it doesn't matter. And there we go. The ICAO standard atmosphere. Hey, it's Rich. Hello, Rich, you there? He's probably somewhere there. I can't see him yet. Okay. Yeah, so there it is, what we've just been discussing. So 1013.2, 15 degrees, and typically 1 hectopascal per 30 feet of drop in pressure. Easy to remember. We all manage that, don't we? But that's what we work off. That's our data we work from.
So there's always 11 hectopascal difference in the QFE and HU, isn't it?
Yeah, that's right. So sometimes it seems like it's, hopefully everybody knows this, but it seems like a mystery to some people here at Elstree that if they've got the Q and H, how we can work out what the QFE is. And if we've got the QFE, how we can work out what the Q and H is. So how do you work out the difference between the Q and H and the QFE at an airfield?
You know what your elevation is.
Yep.
So, and then divide your total elevation by 30, and that difference in the hectopascals.
Yep, absolutely. It's as simple as that. Very, very simple. But it seems to be a mystery to some. So hence we, like Jonathan said, we know it's always 11 hectopascals here at Elstree because it's 332 feet above sea level. So 11 hectopascal, 330. Yeah, easy. So if you go to an airfield and you discover it's only 30 feet above sea level, well, of course, there's only 1 hectopascal difference. So we have heard it before now. I've been to landed at airports or airfields that are at sea level, and they've been given the QNH and somebody's asked for the QFE, and there's a slight pause on the radio. Okay, and then they do actually tell them the QFE becomes the same as the QNH. You can imagine this person write down, oh yeah, lovely, thank you, it's the same, yeah. Because they clearly just never they've just never worked that out. But of course, if nobody ever tells you, it probably, it's one of those things you might not have ever picked up on. I hand on heart, I don't think back in the early days I knew that and realized that until eventually it's pointed out. I was like, oh yeah, never realized that. So anyway, there we go. However, of course, there could be deviation from that international standard atmosphere, and that's really what this slide is all about. Just showing you that, for instance, up at 1,000 foot here, up at this maybe landing site, it's actually 20 degrees up there, whereas according to ISA, by the time we got up there, that should be down to 17, shouldn't it? Sorry, 13 degrees.
Yeah.
So therefore, the difference is ISA. You're in the way. ISA +7. Yeah, easy. And of course, you'll get exam questions, or you certainly used to get exam questions that ask you to work these sorts of things out, because then you might use your whiz wheel to fathom certain things out. But it's nice and simple when we put it like that. Just start off with what should be normal, decrease per altitude, but see the temperature difference. Okay, so it's just a little short video clip for a moment that I plucked off the Met Office some time ago, if it's going to play. Hi, Rich. I haven't seen Catherine's uncle for ages. Come on. So it's just a simple little, but again, when we teach people, we often assume that everybody knows what water vapor is, how it's maybe formed, where it comes from, and so just a nice little simple one just to explain that. And one of the impressive facts I like there is the weight, 500 tons. It's quite significant, isn't it? We kind of forget about that.
Imagine flying through 500 tons.
Yep,
500 tons.
exactly. 500 tons of basically water up there, isn't it? Yeah, very much so. So of course that explains why sometimes when it rains, it really rains a lot. But also think about when that water comes out of the cloud and falls out of the sky, it's going to displace all that air, isn't it? We start to look at things like downdrafts, gust fronts. If that rain managed to evaporate, then we get microbursts from it and all sorts of weird and wonderful things. Okay, so just moving on, just a few types of cloud formations and roughly where you can find them. And there's obviously quite a few permutations, and this is not all of them, but this is kind of like the classic ones, if you like, that you might come across. So out of these, which one is typically rain-bearing?
Nimbus.
The one with nimbus in the name.
Yep, good, absolutely. And of course, if anybody's seen something like Harry Potter, that's why his broomstick's called that, isn't it? Yeah, so anything with nimbus in the name would be suggested that it's rain-bearing. So what do we call one of these, but without the nimbus part? It's just cumulus, isn't it? But again, believe it or not, there is often a bit of misunderstanding as to the difference between, say, cumulus and cumulonimbus cloud. And we usually know that a cumulonimbus, abbreviated CB, is also what sort of cloud?
Storm cloud.
Storm, yeah, thundercloud.
Yeah, that's right. So we can kind of, if we see CBs in the forecast or in the actuals, it's not good news, is it? We want to try and steer away from those. And if it says embedded, what does that tell you?
Coded from?
It's hidden within other clouds.
Yeah. So embedded CBs, yeah, that's not great because you can't even see them now. So at least one of these, you can see this for miles, and you can just make sure you avoid it and don't go upwind of it, etc., etc. Sorry, downwind of it. But yeah, when it says embedded, it's kind of, right, well, you can't even see them now. There are sometimes some telltale signs of them. They really disturb the cloud underneath them that's embedding them, but not always. Oops, it's going to get stuck again. Come on. So your stomach. Was it? I thought it was the water cooler. So this is just a photo. It's just quite an impressive one. So this is very, very high level, possibly, over 30, 40, maybe even 50,000 feet up. This picture was taken, but it's just an impressive one.
That's why you can fly above a storm cloud.
Yeah, we can never get above them. That's right. Okay, and that leads us quite nicely onto things like we talk about in MET, the life cycle of a thunderstorm. We've got the sort of the beginning, the middle, and the end, but we would typically say more like the cumulus stage, which is where it's accumulating, the mature stage, which guess what is the mature part where it's all the actions happening, and then some sort of end, the dissipating stage. So 3 stages of a thunderstorm. So without reading too quickly through all that lot, what do you think is the most the worst stage, or the one you really want to avoid the most?
Mature stage.
And why is that?
Going in all different directions, updrafts, downdrafts, rain in general, lots and lots of turbulence everywhere.
That's where you get lightning.
Yeah, absolutely. And that's where we get that horrible stuff that comes out of the cloud, which is
Rain,
Lightning,
and
Hail.
thunder,
Wind shear.
and
ice, potentially.
yep,
Have
torrential
they?
rain and ice. Yeah, and possibly whopping great big hailstones. And whilst we don't want to sit here and be all doom and gloom, but all those things, they're really not good news, are they?
Yeah.
You know, hailstones sometimes. I mean, I have so far in the UK in my lifetime seen hailstones nearly the size of golf balls. Quite impressive. One year, long time ago, they were like big. Like, you can imagine those striking things like your main rotors, your tail rotors, or your
I've never seen
windscreen.
them that big, but I can imagine.
Yeah. And we're bombing along. So yeah, I mean, it can just obliterate your windscreen, rotors, damaging those sorts of things. So yeah, we really need to avoid that. Why might we want to avoid this stage, the beginning, the cumulus stage?
Did you get sucked in by the updraft?
Yeah, because as glider pilots, you're actually looking for those, aren't you? Trying to find the updrafts. But you're right. Yeah, you know, some of those updrafts can be significant. They could potentially be, you know, going up quicker than what you can actually come down, potentially. You know, going to the extreme. So we do want to try and avoid those where possible, and it can get a bit bumpy otherwise. But of course, that beginning, that cumulus stage, there's usually nothing nasty coming out the cloud. It's only going upwards to catch big old updrafts and those sorts of things. What about the dissipating stage?
Just started reading texting. So you click my memory. Oh, yeah, I'll do that. So yeah, you run me.
Got to be careful of the downdrafts.
Can't tell who it is. Yeah, that's right. I mean, they shouldn't be significant, Tony, but you're right. You know, if it's raining, for instance, as we already said, there will be potential downdrafts. If it's a very warm day, as that rain falls, it can evaporate. Can anybody remember what that's called? If the rain falls, evaporates, and never quite makes it down to the ground.
Virga.
Yay, Virga, that's it. Or Virga, Vigra. No, Virga, that's it. Sorry. And that therefore can, because as it evaporates, it absorbs latent heat or heat from around, which means it really cools the air underneath, and cold air likes to be hot. Cold air likes to drop, doesn't it? Yeah, and quite significantly. Hence, you can get those severe downdrafts or microbursts, those sorts of things underneath them. So whilst the dissipating stage is meant to be quite benign, it can, you know, something, it's an area you still, yeah, you want to probably avoid it. Could be drizzly, so you can't see very well, all those sorts of things. But yeah, the life cycle of the thunderstorm. It's gonna... And another little clip. Fronts, another mystery to everybody normally.
Airport. There is a weather front just gradually pushing its way northwards through Thursday. It's a warm front bringing milder air across the south.
Yeah, weather fronts. When I was learning to fly, you know, this was just a complete mystery to me at first. Trying to get get my head around the difference, because like a lot of people I teach, everybody assumes a warm front is warm and a cold front is cold, but it's just the different temperature, isn't it? A warm front can still be cold, but it's not as cold as the cold front, if that makes any sense, or the cold mass of air. And when you start to understand that, it makes a little bit more sense then. So, and of course, predicting how these warm fronts, cold fronts, occluded fronts move is really, really difficult, because they don't just move across. They can slide, they can dissipate, they can intensify, they swirl around. It's not easy. But one of the things to remember is that if a cold front's approaching, you can't. This is not an absolute golden rule, but a cold front approaching is actually not that bad at all, in the sense of if you wait and it passes through, there's a hefty chance on the other side of it it's going to be really nice weather. We had one just the other day passing through. The weather got bad quite quickly. It swept through fast, and it was gorgeous behind. Absolutely lovely and clear and beautiful. No problems at all. But when they tell us a warm front's coming, you think, oh, here we go. It's going to last probably for ages. As you can see, the cloud just slowly gets lower and lower. Eventually, it starts to rain, poor visibility, and it can take a long time for it to finally pass through. An occluded front.
Just to let you know, I've got to shoot off. Got to go work, unfortunately.
Oh, no worries, Tony. Well, thanks for joining when you could.
No worries. I'll see you soon.
Yeah, see you real soon, Tony. Bye.
Take care. Bye. Bye.
And occluded fronts, maybe slightly better than warm fronts, because they do sometimes pass through a bit quicker, but they're not ideal by a long shot. So it just gives you a little bit of a thought process as to what is heading our way, as to whether we're going to get away with going flying, or we can sit and wait it out, or whether we just need to stay on the ground, or what's likely to happen. Anybody got any questions on fronts?
No, that actually helps explain things better, if I'm honest.
Oh, that's good. I'm glad to hear it, because sometimes, as an instructor, we fall into that trap of assuming you know all this stuff already, and we mustn't do that. That's why sometimes I do quite like showing the relatively simple explanations of videos, so we can then make sure there's not a gap or a lapse in somebody's knowledge that we can plug, and then we can carry on getting more in depth.
Well, the bit about occluded front, that of the fronts is effectively catching one another up.
Yeah.
Like, oh, right, so that's what it is. Because 10 minutes ago, or even a year or so ago, if you'd asked me what's an occluded front, and I'd be like, the best I could explain would be, well, it's a mix of hot and cold. And if you asked me to explain how it works, I wouldn't have a clue. But now seeing it, it's when one catches the other one up, and it's essentially mixes in. That kind of simplifies the whole thing. So we're here.
Good. I'm really pleased. That's good news. Right, let me see if I can skip that. Hey, this was just one of those interesting questions. Why is the sky blue? Just to throw it out there.
With light refraction.
Yeah, it's refraction, isn't it?
Yeah, that's it. So it's one of the colours that actually, it comes through, isn't it? What we get to see. Cool. And I can't remember if I have the next slide. But why is the sea blue?
It's a reflection of the sky.
Yeah, it is. Did you hear that?
Yeah.
I hope everybody knows that. It's usually just a reflection of the colour of the sky, isn't it? It's
very grey and cloudy.
I was going to say, if it's cloudy, the sea's not normally blue, is it? And around some of the coastline, it's usually brown as well. But that's a completely different reason.
Yes.
Oh dear. Okay, who's heard of the phone wind effect, or the phone effect? I can see Rich nodding. I should hope so. Yeah, and it's another. When it's explained, it is quite simple. You can see in that first diagram, if you've got a mass of relatively cool air that's moist but can hold the moisture, but gets forced up. Well, we already know that generally speaking, when you go up, things get colder. And if that air gets colder, it can't hold the moisture as well. But if it manages to rain, it's losing a little bit of that moisture content. So it can then hold on to the moisture, so it stops raining. But then as the wind drops back down, because it's lost some of that moisture content, it'll effectively warm up a little quicker than it did on the windward side. Now, that's a very rapid explanation, which is just showing you there. But it does explain why sometimes if you, a really good example of this I always tell people is the Isle of Arran, because it's quite small. It's often raining because it's up near Scotland. And if the wind blows a particular way, like west to east, for instance, it has to go over some quite big hills. And if it's raining one side, if you literally just get in the car and drive around the other side, there's a hefty chance it'll be warmer and drier. And it works. It does work. You can literally go to the side of the island where that's on the other side of the weather, and it works perfectly.
So is that because the clouds trapped on one side of the mountain or something?
No, it's about, remember how Jonathan, again, you might not be able to hear Jonathan here with me. He's just asking, is it because the mountain traps the cloud? No, it's about orographic lifting. It forces that air upwards and it forces the air to cool. And the cooler air can't hold as much moisture as warm air. So although it doesn't gain any moisture, it can't hold the amount that it already has. And so it falls out as rain, as we know. It condenses up and water droplets and down it, and it falls. But in essence, it's dried that air up a little bit. So it's slightly drier now. Then as it goes over the top of the mountain, as it comes back down, the temperature starts to increase, but it's already dried it out. So the action happens a little bit earlier and a little bit quicker. So it gets a chance to warm up a touch.
Nature's dehumidifier.
Say again?
Just dehumidifier.
Yeah, absolutely. Yeah, literally, that's what it does. And we see this. Anybody flies near Elstree, can you tell me where we see this happen as well around here?
Maybe around Princess Risborough and Chinner, sort of that area.
Absolutely. Yep.
Elevation we have there.
So there's a ridge that sort of extends from around Hitchin area through kind of Luton and down to the sort of the Chilterns, etc. And it goes from low ground to high ground. There's a very distinct ridge, and if the wind is such that it's more of a kind of a westerly, maybe even a northwesterly, it hits that ridge, and if that air is quite moist, it forces it up, and boom, there it is. There's literally a line of cloud over the top of the ridge, and it rains. But then a little bit further this way, there's no cloud. It's perfectly all right. And it does catch people out. You know, they head off out of Elstree, head over that way in what's relatively nice weather, and there it is sitting over the top of the ridge is this whole load of cloud that's raining. And it's basically the same effect, pretty much, but we don't necessarily feel the warmth on the far side as such like you would do here. But guess what? This crops up in exams, so I thought I'd better show you. Oh, I can't remember what's next. Oh, yeah. Okay, one of the greatest mysteries to all mankind, it seems, or pilots, the Coriolis effect, because we come across it in many stages.
If you've ever watched the news during a hurricane or wintertime nor'easter, you've probably noticed that big storms spin over time as they travel. In the northern hemisphere, they spin counterclockwise. But if you were watching a storm in the southern hemisphere, you'd see it spinning clockwise. Why do storms spin in different directions depending on their location? And why do they spin in the first place? A storm's rotation is due to something called the Coriolis effect, which is a phenomenon that causes fluids like water and air to curve as they travel across or above Earth's surface. Here's the basic idea. Earth is constantly spinning around its axis from west to east. But because Earth is a sphere and wider in the middle, points on the equator are actually spinning faster around the axis than points near the poles. So imagine you were standing in Texas and had a magic paper airplane that could travel hundreds of miles. If you threw your airplane directly northward, you might think it would land straight north, maybe somewhere in Nebraska. But Texas is actually spinning around Earth's axis faster than Nebraska is, because it's closer to the equator. That means that the paper airplane is spinning faster as well. And when you throw it, that spinning momentum is conserved. So if you threw your paper airplane in a straight line toward the north, it would land somewhere to the right of Nebraska, maybe in Delaware. So from your point of view in Texas, the plane would have taken a curved path to the right. The opposite would happen in the southern hemisphere. An object traveling from the equator to the south would get deflected to the left. So what does this have to do with hurricane spinning? Well, at the center of every hurricane is an area of very low pressure. As a result, the high pressure air surrounding the center or eye of a storm is constantly rushing toward the low pressure void in the middle. But because of the Coriolis effect, the air rushing toward the center is deflected off course. In the northern hemisphere, the volumes of air on all sides of the eye keep getting tugged slightly to the right. The air keeps trying to make its way to the middle and keeps getting deflected, causing the entire system to spin in a counterclockwise direction. In the southern hemisphere, where the Coriolis effect pulls air to the left, the opposite happens. Storms spin around the eye in a clockwise manner.
And again, hopefully another fairly simple explanation of the Coriolis effect when we talk about which way the airflow rotates around highs and low pressures.
Should be really the Coriolis effect, not Lis, because he's a French guy that discovered it, right?
I guess so, yeah, maybe. But
just checking.
Just checking. Yeah, no, Sophie's nodding. She's like, yeah, that should be. But yeah, sorry, we tend to say Coriolis effect, but Coriolis. Yeah, and like I say, we come across this conservation of angular momentum not just in weather, but we come across it in principles of flight and in aircraft general knowledge as well, when we talk about the Hooke's joint effect and things, blades leading and lagging. So it does explain that anti-clockwise around a low pressure, if anything's being sucked towards the center in the northern hemisphere. Because have you ever heard about the experiment with sinks and plugs? You fill up water in sinks and you pull the plugs out, and theoretically in the northern hemisphere the vast majority will go anti-clockwise. And it is true, it should do that, even though the effect is very small over that small area. The problem is we can't replicate, we can't do this perfectly, we can't remove a plug perfectly without any other influences. And so there's a hefty chance that it'll be more 50-50 as to whether it goes clockwise or anti-clockwise, and then vice versa if you're in Australia, for instance. But the theory behind it is all correct. It is true. It is quite right.
I once traveled through Africa, and I stood on the in that continent where the equator was, and the chaps there and a little tourist trap thing set up with buckets of water and everything, and they just go, okay, here, look, on this side it's going counterclockwise, and they fill the bucket and goes across the line, they plug it, see, it goes the other way around. So that'll be $50 because we showed you that.
Yeah. Oh, that's crafty. With a careful little swirl just in the right direction as they.
Yeah. It's imperceptible. It's like a sleight of hand. Yeah. It's like, ooh, that's
wow, look at that. Oh, how fun is that? Yeah, very good. And so therefore, one of the sayings you might have read about already if you've been studying is about drifting right into danger, because it's suggestive if you're drifting to the right, somewhere kind of ahead of you is a center of low pressure, which is usually not great.
Quite a low out below, isn't it?
Yeah, that's right. It's another, it sort of forms all part of it.
Standing on the wind behind you, the low pressure is to your left.
That's it, yeah. So boy balance law. Yeah, that's it. So Jonathan was just saying, yeah, if you've got therefore the wind behind you in the northern hemisphere, the low pressure theoretically is on your left, and the high pressure is on your right. So the potential better weather is off to your right, potentially. But of course, it's over a big scale normally. We're not talking, 10 miles up the road, are we? Not normally. Depends whether the centre's getting really close to you or not. Okay. So
Yeah, the question is, what was the thing with the drift?
Oh, so if you're in the northern hemisphere, and your aircraft is, this is over a large scale, Sophie, but if you're drifting to the right, remember, cyclones are turning anti-clockwise, aren't they? So if you're drifting to the right,
anti-cyclones.
Yes.
It's clockwise, isn't it?
Cyclones. So sorry, I just got it around the wrong way. Yeah. So we're turning anti-clockwise with a low in the center.
Yeah.
So you're drifting to the right, but over a very large scale.
Okay.
But it's not, the problem with the Met is it's not necessarily an exact science, is it? Because there's too many randoms and variables, which is why even after all these years, they struggle sometimes to predict the weather on an hourly basis, never mind about on a daily basis. But generally speaking, just generally, it's one of the things that's mentioned in the books. You drift right towards danger, or drift right into danger, because it's suggested that there's therefore somewhere ahead of you is a low pressure, which might not be very nice weather, because you're being swirled around to your right, anti-clockwise towards a low pressure.
Thank you.
So drift right into danger works in the northern hemisphere, but the southern hemisphere would be drift left into danger, and it doesn't sound quite as good, if I'm honest. Right.
Australians probably say the same about us.
Yeah, probably. Yeah. Okay, how do we measure cloud cover? We say it's cloudy.
Yeah.
Very cloudy, or not very cloudy.
You break it into octaves or eighths, don't you?
Yeah, that's right. So we typically, there are other ways, you can see, but typically we use the octa scale, and so we divide the sky. I usually describe it. You're on a hill, lay on your back, look up, and with your peripheral vision, you can virtually see the entire sky, give or take a bit. Then you would look at the cloud, assuming there is some, and you try and like scoop it all into one area and just see how much of that entire sky you can fill up. And if you can push it across and you can fill up half the sky, well, there we are. You've got 4 eighths, 4 octaves. But if it only fills up a quarter, you've only got 1/4 of that sky, and so forth. And you can kind of, that's a way to imagine it. And that's exactly it, isn't it? It's how much cloud cover there is. But it's trying to remember how many octaves equals, for instance, few or scattered or broken or overcast. And it's one of those things that come across time and time again. People say, you know, how do you remember it? Well,
1 to 2 is few, so at least that one rhymes.
It rhymes, good, that's it. So we got the obvious ones are sky clear, well, 0 octaves. And of course, if the thing's overcast, well, that's 8 octaves. So that's easy. That takes those out of the equation. And like Gerhard said, 1 to 2 rhymes with few. So great. Even I can remember that. So that's good. So we've only got 3, 4, 5, 6, and 7 now. And if you can just remember either A, that broken is 5 to 7, or scattered is 3 to 4. And that's how I used to remember it. Few 1 to 2, scattered 3 to 4. Because I remembered it followed the same, just 2 sequence. Then it left 5 and 7, which had to be broken. Bingo, I managed it finally. But even after all these years, that's exactly how I would remember it.
Yeah.
Is it desperately important for us? Not.
Can be, depending on what we're trying to do.
Remember.
Yes. So, you know, I just said to Jonathan and you guys, is it really important to remember? It might be. Why?
Comparing what you're seeing outside to what was forecast.
Maybe. Yeah.
So for changing conditions.
Cloud in the way. And one of the things you don't do in helicopters is find the cloud.
Yeah, absolutely. But let's just, John's just saying obviously about not flying into cloud. Yeah, absolutely. You know, if you're heading towards an area where the cloud is going from sky clear to few to scattered to broken to overcast, especially if it's low level, that's a big problem. So that's certainly one thing. What else? Something else that might not be so obvious is what about
sunglasses, sunshine?
Yeah, see, when we take people up flying, they always assume that the clear sky is the best day to fly. It's like, well, you know what? Actually, if you're flying towards the sun, it's awful because it's really bright. You're squinting. You can't see very well sometimes. If there's a bit of moisture in the air, it's hazy. When actually an overcast day is really quite good because you don't get any of the sun in your eyes. Don't need your sunglasses. You can see usually really clearly. So of course, if you're going flying and it's overcast, but maybe the cloud is thinning out, you're heading towards the west in the afternoon, especially this time, you're probably going to want your sunglasses with you because you're not going to be able to see very well. So it'd be really important to know about that. Or if that cloud, 1 minute it's covered, then it's not, so the sun keeps glaring through, all those sorts of things. Yeah.
Also, ability for other aircraft.
Yes, because remember, we're not trying to punch through that cloud. We're not trying to go above it. So no matter what it is, we're just going to remain below it. However, if we do see in the METARs that there's just few cloud out there, it generally means it's just so small, so spread apart, that even if that few cloud is quite low, it might be perfectly safe to be above it because it's just so spread out, it's not a problem. But you want to make sure, of course, it doesn't start to develop into scattered cloud. You know, for us, for what we do, flying above scattered cloud is not a good idea. This is a quick way to get caught out and end up above the cloud and not being able to get back down again. So few I'd be okay with, but scattered, no, we should be underneath that. That'll already start to be too much and obscure the ground and all those sorts of lovely things. Cool. Any questions on octas? Marvelous. So what's this then?
Speed.
Yeah, it's a UK one for a start off. Low level spot wind chart, also known as a Form 214 or F214 as we often call it. Is it an actual reading or is it a
best guess?
The best guess. It's a forecast. Yeah, that's right. And it says so at the top. So of course, if all of these forms that we use, don't just jump straight into, oh, I know where we are. We're down here and it's going to be, 2,000 foot. You better check that it's actually valid for a start off. Seen that many a time. Somebody grabs an old printed out one on a table and starts using it, and it's the one from yesterday, for instance. So always double check the validity of that form, when it was produced and when it's valid for, or the times it's valid between. Make sure the date's correct on it. So you can see this is quite an old one now, 5th of May 2020. Yeah, and it's giving you its best guess of what the wind will be at those different altitudes, either 1,000, 2, 5, 10, 18 or 24,000 feet, and a lat and long position, and it should coordinate pretty much with that little cross, for instance, there on this particular box, which is a bit north of where we are. So this is the one we would normally use. We might look at the ones near us, but these are quite far away. So when you are looking to go hovering, we wouldn't necessarily worry about a Form 214, probably not even for circuits. But if you're going to go and navigate somewhere and you're going to be up at, say, 2,000 feet, yeah, we need to know where that wind's coming from, because of the amount we're going to drift, or if it's a headwind, we're going to be flying slowly across the ground or quick, etc., etc. So this doesn't tell us the surface wind, does it? Just to make sure everybody understands that. Happy with that, Ross?
Surface winds?
Yeah, so remember, this does not tell you the surface wind.
It does not.
No, this is the upper wind. Remember, this starts at 1,000 feet.
Right.
It doesn't start down on the surface.
Yeah.
And vice versa. I have caught occasionally people doing a navigational plan, planning to fly at 2,000 feet and looking at the surface wind for how much drift they're going to get. It's like, whoa, that's the wind down on the surface. It's probably completely different to the wind you'll experience at, say, 2,000 feet. So this is far more for navigational purposes, Ross.
Yeah.
But it's one of those things that we can look at every now and then, even if we're not going very far, to get a bit of a feel for what the wind is typically doing, where it's coming from, how strong it might be, those sorts of things. But it's not how we would traditionally look at the local weather for just flying around as such. But it's worth knowing. But definitely for planning for navigation, without a shadow of a doubt, we use these sorts of things, this information.
Oh,
Yo.
Surface wind should go up to 2,000 or 3,000, shouldn't it?
Well, it depends what you're talking. What do we mean by the surface wind? I mean, normally we're looking at all of our local airfields, terminal maneuvering areas, and terminals, sorry, like Stansted, Luton, Heathrow, those sorts of places, to get a feel for what the surface wind is, because of how choppy, how gusty it is, and whether you should go flying or not for a start off. Because the surface wind is usually, but not guaranteed, but usually far more turbulent than the upper winds.
Yeah.
So when we send you guys out solo, we usually want to make sure the surface wind is ideally, to be honest, less than 10 knots. Now that
Okay.
upper wind, when you go flying at 2,000 feet, that could be 20 knots or more, but it might be very consistent. But you're not trying to hover. You're not trying to do low-level maneuvers, are you? You're up in the air. So the stronger wind is not such an issue other than just simply drift, for instance. So this is nothing to do with surface wind. And what is this?
215.
Hey.
Forecast.
So it's another forecast below 10,000 feet for that area, the UK, for instance.
Yeah,
But
so,
remember,
sorry, Paul. Yeah,
that's
what,
okay.
what the
Just
weather is.
It's another forecast. Don't forget to check the validity of it, as always, before you use it. But it's a fairly broad forecast. I mean, for instance, in this, if you happen to be in area A, it's a huge, massive area, isn't it, that it's forecasting? But it's only because they seem fairly certain what the weather is likely to be there. Whereas these different bands down here, B, C, and D, are a lot smaller, even though they span over maybe quite a distance. They're not very deep, so it looks like the weather's moving in that south westerly direction. So it gets broken down. So I once heard somebody say about, oh, there's going to be quite a bit of cloud. I was like, how do you know? I said, because these lines here, these wiggly lines. But that just depicts the difference, the different zones, the different areas of the forecast weather. What's the arrow for?
Is it showing the direction that high pressure system is moving?
Yeah, that's right. It's exactly that. So
Five
saying
knots.
this classically or typically this area is typically moving in that southeasterly direction at about 5 knots. In other words, not very fast at all. So from that, we could probably deduce that the weather is not going to change rapidly because it's just not moving very fast. It's a high pressure area, which is usually fairly calm. Yeah, that's it, fairly stable. Doesn't mean to say good weather though, does it? It just means it's not necessarily going to change quickly. So if it's an area of misty, murky, horrible, poor viz, it's probably not going to change very quick. But if it's a beautiful, clear one like we've got at the moment, brilliant, because it's just not going to change very quick. And that's another thing we come across, and I think I thought the same thing. You know, high pressure meant good weather and low pressure meant bad weather, but it doesn't quite follow. There's too many other factors that are involved in it. And of course, we've got some of those coloured lines here. Let's say they're not always blue and red. They can be pink as well, as we can see. So what sort of a front is this?
Included.
It is an occluded front. Yeah, it's a combo, isn't it, of the little triangle cold and the little semicircle warm. So it's occluded front. But it depicts typically the direction of the front. So it's suggesting this front is moving somewhere along the lines of this direction, and this one is moving that way. So that's kind of like the pivot point. But the one thing to remember with fronts is they don't just move, they slide as well. So they can move and slide and change. And that sort of messes with your mind a little bit because the whole lot's shifting sideways as well, possibly at the same time. It doesn't mean it's spinning around that one spot. Does anybody want to have a little go, if you can read it okay, at decoding area A for us? This lot here.
I'll give it a go.
Hey, go on, Lewis.
So area A, the bulk of the UK, you've got 30 kilometres of viz, nil significant weather with isolated hill fog. So in hilly areas, up the mountains and that, also probably down in the Chilterns and that. Cloud, occasional, isolated on the land from 1800 Zulu time, scattered and broken. And we got cumulus, stratocumulus with moderate icing in turbulence from 2,000 to 3,000 feet, and again at 4,000 to 5,000 feet. With 0 degree freezing point at 2,000 to 4,000 feet and 5,000 to 7,000 feet in the far southwest.
Very good. Yeah, well done, Lewis. Very good. Yes, that's well done. So we we realize it's broken into columns. The first column just depicts the actual area you're talking about. The next one is surface visibility and weather. Then, of course, the cloud you're going to experience there and any maybe turbulence. And then the isotherm in that in that fourth column. Very good. Yeah, nice one, Lewis. Who wants to have a go at this nasty one down here then? Gerhard or Sophie, do you want to have a crack at this?
Yeah, I'll give it a go. So again, D is all the way down there in the bottom left, and that little patch there under the water, it would seem. It says 30 kilometers, visibility, no significant weather, isolated, occasional, I don't know, CCOT, don't know that one, with 7 kilometers of showers and rain showers, isolated at 3,500 meters with heavy rain showers and thunderstorms, I think. Again, CCOT, not sure what that is. And land, not significant, I don't know what land is, but until 1900 Zulu, isolated hill fog.
Yeah,
I
Gerhard.
guess it's on that. Not there. Yes.
Yeah, that's good. Well done. Sea and coast.
Oh, sea and coast. Right. Yeah. I guess it's because I never go that far down in this thing to read it. I'm always concerned with where we are. Okay, sea and coast.
And that was heavy showers and rain.
And rain.
Because the showers are slightly different from rain. Showers are possibly intermittent and rain is continuous. But that's really good. And heavy thunderstorms and rain.
Thunderstorms, right.
Okay. And so it's saying around the sea and coast and the land until maybe 1900 Zulu. So that's good. Yeah, well done. Try the next one then, Gerhard.
Occasional scattered, broken, altocumulus, moderate severe ice and turbulence at 8,000 feet until wherever, all the way up west.
In excess of 10,000 feet and out to the west, yeah.
Occasional scattered, broken cumulo and stratocumulus, again severe icing and turbulence at 2,000 to 4,000 feet and 7,000 feet to 10,000 feet. Isolated cumulonimbus at 2,000 feet to 4,000 feet up to 10,000 feet along the sea and coast. And land till 1900 Zulu, isolated, scattered, broken stratus clouds at 500 feet to 1,000 feet, and again at 1,500 feet, sea and coast.
And then
freezing point is 8,000 feet to 10,000 feet.
Yeah, very good, not bad at all. Just watch out because this was moderate, not severe icing, but yep, you're all on the right lines. The key's over there, of course.
Yeah, moderate turbulence and icing. Yep.
It's really small on my screen. Yeah, very good. In other words, not very nice weather.
No, I wouldn't advise it in a light aircraft.
And I'm not surprised because, of course, it's very, very close to that occluded front, isn't it?
Yeah, there's a lot of disco happening there.
Yeah, good. Why are we just a curiosity? This isotherm down here, the freezing level. Why does that matter to us at all, or?
Yeah, icing.
Yeah, carburetor icing, and depends on how you're going to fly, I guess. But in A, especially with 2,000 feet, easy, no problem. So just got to look at the carburetor icing, especially, and of course, icing forming on the airframe. Right, you can have icing forming on the airframe and so forth. Yeah.
Remember, carburetor icing can form in potentially even up to 30 degrees. Now, admittedly, generally, the colder it is and the damper it is, the more prevalent carburetor ice is until it gets so cold it's no longer ice. It's no longer going to form because of the moisture content's already frozen. But so this is all to do really mostly with airframe icing on your rotor blades, which is very bad news. So, of course, we can fly in sub-zero temperatures, and I dare say it won't be that long before maybe we start having some sub-zero temperatures, especially early hours in the morning. Doesn't mean so we're going to suddenly get ice forming on the rotor blades. So if we flew, so let's just take sector A here, area A. If we did manage to fly above, 4, 5, 6,000 feet, and it was less than 0 degrees, does that mean we're suddenly going to get airframe icing on the rotor blades and the airframe? And
no.
No, because
Well, it's all to do with the moisture content, isn't it?
absolutely, yeah, exactly. If there's not enough moisture, it isn't going to freeze, is it?
Mm.
Simple as that. But what do we say? What do we mean, Ross? Do you think by moisture?
Clouds.
Or did somebody say?
Clouds.
Yeah, no, of course we don't fly through the clouds, but yeah, absolutely. If you were to fly in sub-zero temperatures in cloud, and you can get water that's below freezing and not frozen, so you get super cooled water droplets and all sorts of wonderful things like that. So if we were to fly into cloud, not that we should, because it's really dangerous for what you guys do at sub-zero temperatures, yeah, you can expect ice to start forming rather rapidly on those rotors and possibly on your screen. You can't even see where you're going and your rotors get modified. But also, of course, if it rains, it is possible that it can rain in sub-zero temperatures. Now, that rain potentially will freeze on your rotor blades on impact, and that is a big problem. So
rime or impact ice. What's it called? Rime.
Yeah, there's rime ice, there's impact ice, there's clear ice, there's all sorts. So none of them are very pleasant and we don't want to get them. So it is a good idea, especially when we start getting into the colder times. Yeah. Oh, that's where it kind of just develops on the black frost, kind of more or less, yeah. So when we're flying in these colder times, it is a good idea to know where the freezing level is. And we've also got outside air temperature gauges in the aircraft, because if we happen to notice it's sub-zero and there's some moisture content, i.e. it's raining, it's time to descend into warmer air or even contemplate on landing if that's the case, because you do not want that to form on the rotors. It's really bad news. Okay, any questions on the 215?
Just wanted to sort of query it and to double check really with it where it says the XXX. I know that refers to the upper chart limits, which is typically 10,000 feet, but would I be right in thinking that, let's just say column D, for example, so you've got 8,002 upper chart limits. That doesn't necessarily mean it stops there. It could
it's in excess of 10,000. In other words, like you rightly say, it's off the chart.
Yeah,
it could be 11,000. It could be just a smidgen more than 10,000, but it's in excess of. Yeah. It's a bit like having all the nines in the visibility. It doesn't mean say it is 10 kilometers of visibility, it just means it's beyond, it's 10 kilometers or more. So this is 10,000 feet or greater.
Gotcha.
That's it. And about the only other one that sometimes people ask is, what do the dots mean? It's just like, well, it just goes down to the next line. It means it hasn't finished. It's just the box is not big enough to carry on the line. Occasionally people have asked. I have seen an exam question, by the way. So this will test you all, your ability to interpret all this weather. What is the outlook?
Oh, right.
Outlook until
yeah, it's just down there. I haven't seen that question for a long time, but there's an exam question. What is the outlook? And you're like, oh my god. It's just at the bottom of the chart. Yeah, so it tells you what is the outlook likely to be, and you can see there, according to that, similar. Yep, similar.
Is it because like in area A, it's slow moving, and like I say, it's not going to change much? So
yeah, and even B to C to looks like possibly down to D, it's not moving very fast. This is all just a bit slowly kind of shifting around that direction, isn't it? So yeah, it's not going to be a fast moving weather system particularly, because it looks like the high pressure will start to dominate maybe. All right, TAFs and METARs. Oh, another mystery. So what's a TAF and what's a METAR?
A TAF is a terminal area forecast, and a METAR is that's a good question.
Meteorological airman report.
It's close enough. Yeah, oh, that's good. Jonathan said it. So METAR is an actual report, whereas the TAF, as we know, is a forecast. So forecasts and actual reports. And we do want both of them, don't we? We want to kind of know what's likely to be happening or going to happen, but what is actually happening right now. And we can see here's just an example for Heathrow. Oh, do you ever why is Heathrow LL? Did you ever hear an explanation about that? About the best.
A long time ago, it's a historic thing, but I don't know why it's EG for England. Isn't it?
So EG's for England, so it just denotes that this ICAO is for England, and LL, because some of them are blatantly obvious. The two letters sound almost like the airfields, but LL, the closest I could ever get to was location London. I found something about it. That's it.
It was, well, just London Airport once upon a time,
Yeah.
wasn't it?
Yeah, so I think it just got London location or I think it said location London, i.e. London Airport. Gatwick, yeah, so that makes perfect sense, doesn't it?
Yeah.
And there's some others that sound absolutely correct, you know. Okay, so that METAR, does anybody know what the COR is?
Oh, blimey.
No,
No, I was going to say correlated, but no, I don't know.
Corrected.
Yeah, it's
Corrected,
obviously been kind of like corrected for some, maybe a mistake or something, so it's a corrected one.
Ah,
And then it just goes through the whole EGLL, so it's definitely Heathrow.
on the 5th.
On the 5th, 1550 Zulu, so that's when it was created automatically. Yeah,
100 degrees at 40 knots.
there it is.
4 nines.
So visibility in excess of 10 kilometers.
No cloud detected.
Yeah, no cloud detected. Well done, Jonathan. How about these two?
It's 14 and -02.
Yay,
so
good.
That's the
So this-
difference.
This throws people sometimes.
Quite a big gap, actually.
The M is minus. Yes, it was a massive gap. Yeah. So -2. So the M sometimes throws. What about this one?
The QNH.
H.
And
Significant weather change.
no significant weather. Good. And then the TAF, you're all in the way. I'm going to have to move you a second. There we go. And the TAF for London Luton. Correction, sorry, Heathrow, location London. On
Zulu,
the 5th, created at 10:52.
52 Zulu, and is that validity for the 5th at 1200 Zulu until the 6th 1800 Zulu?
Good. So how long time span is that, Gerhard?
Almost 24 hours. It's about 16 or 18 hours, I think.
It's over, isn't it? It's greater than.
Oh no, sorry, you're right. It's greater than. You're right. Math is hard. Yeah, it's more than 24 hours. Yeah.
And it's because, as you can probably see by this, there's probably no real great weather change.
Yeah.
So they're a lot better at forecasting over that greater period of time. Otherwise, you can get some really short ones when it's changing rapidly, and they're struggling to forecast it. So this is a sign that there won't be significant changes during that period of time necessarily. Cool. So
0 degrees, 12 knots wind, visibility all good, over 10,000. Few clouds at 2,500 feet. Probability 30. Now this is the one I always struggle with, but in the next 30 minutes, I guess temporarily. Tempo between 05 1200 between the 5th 1200 Zulu and the 5th 1500 Zulu. What is that? 090 winds 090 at 15, gusting 15 at 25 knots.
15.
There's a
Yeah.
30% probability. Is that what it is?
Second.
Prob 30 means 30% probability of that temporary condition existing between those times.
Oh, hold on. So there's only ever two probs, probability 30 and probability
40.
40,
and
yeah.
that's where the split is. And trying to put this across to people, it means prob 30 means there's a 30% chance or less. So there's less than 30% chance that this is actually going to happen, and it's highly unlikely. However, it could do. And if you see a prob 40, it's 40% or greater, which means it probably is going to happen. And that's the split. That's it. There's no other split.
Okay.
30 or below or 40 and above. But 30, don't forget, 30 and below doesn't mean say it won't. It just means it's quite unlikely, but there's a chance. But 40, more than likely. How about this tempo then? Now that means temporarily, and we all know temporarily, not permanent. Can you remember the definition of temporarily as far as the Met Office is concerned? It's a tricky one.
30 minutes. That's a 30 minutes rain within the 3 hours frame. That's something like that. 30 minutes.
Yes. So first of all, you need to have a time frame. So 12 till 3. So it's only a 3-hour window when they think this is going to happen. Just this 3-hour window. And temporarily would mean, well, as we said, it's not going to be continuous. It's going to be temporary. But what exactly? Well, it's usually no more than 45 minutes increments, and for no more than 50% of that time period. So that 3-hour time period. So for no more than a maximum of 1.5 hours, for no more typically than 45 minutes at a time, you're going to get this. So that is the definition. I know an examiner has asked that once before. Some poor students on their skills test. Bearing in mind they haven't even got that out of the classroom yet, and the examiner said, "Yes, and what's the definition of temporary?" Like, oh, you know, poor lad.
What
But
about
anyway,
is there another one? Tempo, and I think there is another one, right? Instead of tempo.
You thinking becoming?
No.
No, I can't think of one at the moment.
Okay.
So when you get something like a prob 30, highly unlikely that temporarily, in other words, they think there's a slim chance that during this period there's a possibility the wind might shift slightly and be a bit stronger for whatever reason.
That sounds more likely to, like, looking at the bigger picture of what's between the Meta and the TAF. You can see like the wind is basically backing off both in direction and speed, but they're saying, oh, there's a possibility that in that time scale it might basically not back off quite so much and might gust and pick. That actually sounds more like sort of local, or should I say a brief weather phenomena brought about by, say, topography in the area around London.
Yeah, it's possible. Because I mean, the Met, as far as they're concerned, there's nothing significant, and there's nothing particularly in here. There's no sign of any rain. I mean, it's of course what you can't tell in here about is maybe whether there's any fronts passing through or anything like that. But there's no mention of any rain, is there? Anything like that whatsoever, which can often cause gusts, etc. Gust fronts. So it's just one of those slightly random. Yeah, but somewhere along the lines, you just rightly say there might be. For whatever reason, whatever it is, we haven't got the big picture here, unfortunately. We haven't got the 215 to go with it, so you can't put the big picture onto it either. But that's good. So decoding wise and understanding the difference between the two is very good, because they are very similar at the end of the day, the way they're written. But an actual report, so an observation and a forecast, a best guess. Very good. So you can see that the tempo if it being a Meta or a TAF, is very slightly different, but it's still basically the same thing. Anybody tell me what sort of cloud that is? And yes, there is a little R44 up there.
Oh, that's quite a rare phenomenon, though.
It is, although it's starting to get a little bit more common. We saw, yeah, mammatus. Yeah, when it first got introduced, I'm not sure how long ago it was now, or first classified. It might have only been 15 years ago. It was rare, ever so rare, but it seems like it's just becoming a little bit more common. Or it might just be we're looking out for it more. But we had something the other day. Sue was with me. We were flying, and it wasn't vast amounts, but it was very pronounced just out to the west. It was proper pronounced, yeah. It can sometimes mean it's quite unstable above it. Unstable conditions. Quite impressive to see. That's an interesting one. Anybody want to have a go at that one?
That's a roll cloud.
It certainly looks like it, doesn't it? Yeah, and quite a significant one as well. So literally, if it's animated, that'd be rolling around.
Wouldn't like to be near that.
No. And
Banded, cumulonimbus.
yeah, but it looks like it could be an embedded one because you can see there's low level clouds. So it might be hidden. And this is the bit you can't see, all the nasty bit up the top. And it's often described as an anvil, isn't it? Is there anything interesting about the anvil? Maybe something it tells us?
The overall direction.
Yes, good. So the overall direction is suggestive that it's moving that way towards that sharp point.
Oh, I
Yes,
see.
because it gets pulled by the upper winds. Again, it's not guaranteed, but that's the general gist of it. It's being pulled along in that direction. So it's quite cool because if you can see one, you can see it's pointing away from you. It's great because it's probably going away, and you do not want to be going around that side of it. Out of interest, how far ahead of a CB can you potentially feel the effects of it?
Is it 5 nautical miles?
Oh, no, that's about 20.
Oh,
Yeah,
I was thinking about 30 actually.
it's both pretty good guesses. Yeah, somewhere typically about 10 miles. But I suppose the end it depends on the intensity of it and those sorts of things. But yeah, so it's significant if you're upwind of them. So you don't want to be upwind of one of those. Not a good idea. And there we are. We talk about embedded thunderstorms. I said dangerous because you can't see them. I forgot that slide had some questions on it. Any questions for anybody?
Yeah, I do.
Hmm.
Mechanical turbulence, what is that?
It's mechanical turbulence is caused by the terrain. So it's
Is
the
it-
surface wind blowing over terrain, and then as that causes the flow to become turbulent, then obviously that lifts, and so it's caused by hard things basically. Could be buildings, trees, forests, ridge lines, but not to be confused with orographic uplift, which is something a little bit different.
Okay, so orographic would be with
Larger scale. So you could be downwind of London's business centre, for example, and if the wind is from the west and you're heading out towards the Thames estuary, then you could get some mechanical turbulence off the skyscrapers, for example.
Okay. Okay, thank you.
Thanks, Reid.
cool. Didn't know that. Cool.
I didn't realise it was called that, but it makes sense.
Guys, I was just thinking, yeah, I haven't heard that term for quite some time. I was thinking, I'm sure it's to do with, let's say, just physical things, isn't it? Whereas,
Yeah.
right, say, orographic is over a much grander scale.
I had one a couple of days ago here, so like, ooh, that's far away. Mechanical on the gaps.
Can I just make one comment? I really enjoyed that. Thanks very much. There was a question about surface winds and the 2,000 foot wind, 1,000 foot winds. I think as helicopter pilots, mainly flying VFR, I think understanding that variation between ground level and 2,000 feet is actually really important. So of course the 2,000 foot wind tends to be what's known as the gradient wind, which essentially is how the wind at 2,000 feet, which is considered clear of turbulence from the ground, is flowing across the isobar, so steady state. And as you get closer to the ground, so the turbulence increases, and therefore the wind strength will reduce because of that turbulence, friction, if you like, from the ground. And also it will back because it's getting slowed down, and the effect is much more pronounced when you start doing your night VFR, where that turbulence layer becomes much shallower. So therefore, the 2,000 foot wind essentially comes down, and you can get a really marked change in direction of wind at as low as 500 feet. So the wind, let's say, for example, you could take off with the wind at 270 and then suddenly find yourself with a wind at 240 at 500 feet. Just something which is worth reading into if you've got the time and the inclination. That variation of wind between 0 and 2000.
Okay, but because they were talking about friction layers, and they mentioned, well, I found out that some books refer it to 2000 and some other are at 3. So I don't know which one is.
2000 is the standard that the military uses. That's all I can speak to. Essentially, that's all I've done.
Okay.
But 2000 feet is you're considered to be above that friction layer. So therefore, the wind is as per the isobars, if you like. So you've got the geostrophic wind, which is if you had straight isobars, you would flow straight down the isobars. But because you've got curvature in any normal weather system, the actual wind tends to go across the isobars slightly. So that's the gradient wind. And that gradient wind at 2000, you then that's fixed, if you like. And then as you come down into that friction layer and the turbulence builds up, so that wind will vary from the gradient wind. And basically, just think of it in terms of the lower you get, the more the wind is kind of slowing down, and as a consequence, it's backing. So, and it's a rough rule of thumb, but it's important thing is that at night the change is much more significant than during the day, because during the day you're getting more mixing. So therefore the effect is diluted, whereas at night not. As I said, it can be quite dramatic. It certainly caught me out doing night circuits in the past.
You feel it now we get into the colder weathers. The same as you say, Rich, there's less mixing of the thermal action, isn't there? And if you're over an air where there's less objects in the way, you can encounter that as well, and you don't get that change until you're getting quite close to the ground. Yeah, we're getting a little bit of that now because we're getting far less thermals out there now, so we tend to find a little bit more of that.
Good. That means the gliders are staying away.
Yeah, we were just talking about them earlier. You got all the hot air balloons instead in the morning.
Yeah, true, very true.
On the 214, what I was trying to make sure I put across is, of course, we're using that not to try and judge the surface wind. That's just the upper winds, and we're going to be using things like the METARs and the TAFs for the surface wind judgments. But the surface wind judgment is about that final approach maybe you're making to that confined area, or how choppy it's going to be, and if we're sending you out solar, all those sorts of things. Whereas the upper wind quite often is a much cleaner wind, but it will be different strength and direction.
Yeah,
and these
I must say, I think with the 214, I've never found particularly helpful as a helicopter pilot.
No, not
you're just not
amazing,
covering the distance fast enough. And actually, as a consequence, the METARs and the TAFs are all of more value. Obviously, if you're a fast jet pilot, then you're taking off from the south, then you will cover north to south in one sortie. So therefore, the 214 becomes more important. And likewise, the vertical profile for them becomes more important because they'll punch up to 25, 30,000 feet plus to make that transit as more fuel efficient.
When we're doing when we're doing our navigation calculations, if we're doing it in the traditional method, the film 214 is all we've got to go by for that sort of 2,000 foot wind flying locally. So all your drift calculations are based entirely on that. But it's of course, that 214, if it's a midday one, if you go off in the morning, it could be reasonably different, especially if there's a weather system nearby, compared to what they think it'll be at midday, compared to what it'll be afterwards.
I think you can go into the Met Office website and you can get most airfields weather for the day, which will give you the 2,000 foot winds and temperatures as well. So you could build up your own Met package as you go along, and I think it's free of charge as well. I don't think you pay for that. Can't be certain, having never paid for my aviation in my life. So lucky, I'm the lucky one, I know.
Any other questions, anybody?
I was just going to say, relating to what Richard was saying about the difference between like the wind gradient and on nighttime versus daytime. Is it obviously, yeah, during the daytime you've got the lifting and mixing of the air due to obviously the sun being up, but is the sort of lower gradient or lower level gradient change, as it were, due to the air cooling and being more dense and of higher friction, if that makes sense?
I think it's very easy to overcomplicate these things, and obviously the cooling air will have a difference, but I think the most important issue is that as that mechanical turbulence layer, the friction layer, reduces, so essentially that gradient wind at 2000 is allowed to come down and down and down and down and down. It can come right down as low as 500 feet. So suddenly you on the surface with your surface forecast there, I'll use the example of 270, will come up, and at 500 feet you're actually in the gradient wind because there's no mechanical turbulence that's mixing it, causing it to reduce, and therefore you can hit a wind that's significantly stronger and from a completely different direction, up to 30 degrees off what you had been anticipating. So if you're going up to 1,000 feet for your circuit, that can actually make quite a significant difference to how you're going to plan to fly those angles of bank to map your circuit going round. So I think temperature-wise, I really wouldn't worry about that. It's just getting fixed in your head that you can have that big difference between night and day. How do you resolve that? Well, actually have a look at the 2,000-foot wind.
Yeah,
that 2,000-foot wind will be a really good indication of what those lower level winds are going to be. But most of them, if you see, they give you 1,000-foot wind as well, and that's really useful. And they kind of they do a calculation between the two, and it's kind of as Paul quite rightly said, Met is not is as much an art as a science, and thanks to modern computing and decades of the data accumulation, it can be really accurate. But of course, with climate change at the moment, we're finding that Met is getting caught out time and time again, because all those decades of model building using data from the past in order to generate algorithms that can predict weather in the future are now essentially working on incorrect data. So you can get some real surprises in Met reports. So definitely worth looking at when you're planning your flying in some detail. It will keep you out of trouble, and I know because I've been in enough of it in the past myself in rather unpleasant places.
So sometimes some of those Met forecasts they just change so quick. You think it's set for the day. The next time you look at it, it's already been updated. It's already been changed because they're struggling to predict it.
Yeah. I mean, most of us have been told tomorrow's flying program is cancelled due to the weather report, and then the next morning you look out and it's just blue skies and sunshine and without a puff of wind. Just think, okay, well done, Met man.
So, you think this morning was quite a good example. So there were actually, I suddenly saw last night that they were predicting fog this morning. And of course, the difference between things like radiation fog forming or not forming can be just so small, the minutest little difference, and suddenly it doesn't form, or it does form.
Yes,
so that's
absolutely right.
So difficult to actually say for certain whether it's something is going to happen or not. It's very, very tricky, very tricky.
Yeah.
And when we're teaching you, we want you to just have a good all-round understanding to try and build your picture of what it's likely to be when you want to go flying. And we don't just use that one source of information. We try and gather many different sources from many different places to try and build that big picture of it. That's the basics behind it. Cool. Any other questions? All right. Okay, I'll get an early night. You all right, Jonathan? Sorry, bless him. He's out for the count. He's all right. All right, I'm going to say thank you very much for everybody for It's all right. Pleasure. I'm going to finish off some pizza, I think, quickly, and then head home.
Thank
So
you,
thanks
Paul.
everyone
Getting on the
for
gin
your
tonic.
time. Nice to see you, Rich.
Yeah, you too, Paul. Take care, everyone.
Thanks so much for joining us. Cheerio,
Bye.
guys. See you later.
Thanks, Paul. Very informative.
You're welcome. No problem. It's good fun. See you later.